Chapter 3, Section 5 takes a look back at limits at infinity. So we've previously worked with limits on how to solve limits using different methods. Here our focus is specifically finding limits as x is approaching positive infinity or as x approaches negative infinity. What we're ultimately looking at here is the end behavior of a function using limits. So we have a theorem for limits at infinity, and it says if r is a positive rational number and c is any real number, then the limit as x approaches positive infinity of c divided by x to the r power equals 0. So this is saying that if you have some constant divided by x to the r power and the limit goes to infinity, that's equal to 0. So an example would be the limit as x goes to infinity of 5 over x squared. What's happening is, as x goes to infinity, the denominator gets extremely large while the numerator is the same. So you would have numbers like 5 over 4, 5 over 9, 5 over 16, 5 over 36, 5 over 100, 5 over an ever larger number. So the ratio will actually approach a value of 0. Same thing happens if we're going towards negative infinity. So our theorem also tells us that the limit is c over x to the r as x approaches negative infinity equals 0. So it's the same concept except it'd be a negative number squared in my example. Okay, so our first example of this, we want to evaluate our limit, and we even have a hint. Divide the numerator and denominator by the highest power of x in the denominator. So when I look at this, I see limit as x goes to negative infinity, and this process only applies to when x is approaching positive or negative infinity. We look at x to whatever the highest power of the denominator is. It does not matter what the power of the numerator is. X squared. And we're going to use that to rewrite our limit. So limit as x approaches negative infinity, and I'm going to take my 6x squared, and I'm going to divide it by the highest power of the denominator, which was x squared. I will do the same thing with my denominator, and I will do it on each term. By doing it on each term, it's the same thing as if I had done the original problem times x squared divided by x squared, because that's a creative form of 1. So I'm essentially dividing both sides of my fraction by x squared, so it's the same as if I were dividing by 1. So when I do this, I'm then going to simplify. X squared and x squared cancel, leaving a numerator of just 6. And in my denominator, x squared and x squared cancels, leaving 2 plus. But notice nothing cancels here. So I have 5 over x squared. Now I'm ready to evaluate my limit. Because I'm evaluating the limit notation goes away. The limit of a constant is the constant. So I have 6 over. And then when I do the limit of the bottom, I do the limit of each part. So limit of 2. And then the limit of 5 over x squared as x goes to negative infinity. That's what our theorem talks about. So the limit of that is 0. So I can say this limit is equal to 6 over 2 plus 0, which is 6 over 2, and that gives me a value of 3. So this is what the limit is equal to as x is approaching negative infinity.